In this lecture, I will discuss binary addition and subtraction. Let us first start with binary addition. Binary additions, in binary number system there is only two symbols, that is 0 and 1. Let us find what are the results when we add two different bits. For example, when we add 0 and 0, that means bit 1 is 0 and bit 2 is also 0, that is A and B. The sum will be 0. 0 and 1, when it is added, then it is 1, that is sum is 1, and 1 and 0 again it is 1, and 1 and 1. If both the bits is 1, then the sum will be 0 and carry is 1. Let us take an example. This is decimal number system. As per the decimal number system, we add 8 plus 4, then the sum will be 2 and the carry will be 1. And next, this carry will be forwarded to the next digit and it become 9 plus 6 and another is carry 1, that means 16, and 16 means the sum is 6 and carry is again 1. Now this 1 is again forwarded to the next digit. When this carry is forwarded to next digit, then the result will be 2 plus 1 and this 1, that means 4. Now it is 4 means sum is 4 and carry is 0. Hence in this way it is a class 2 class standard 1 mathematics. Similarly, we can also use the same principle in the case of binary number systems, binary additions. For 1, there are 2 ones, therefore the sum will be 0 and carry will be 1, and this carry is forwarded to the next bit. Similarly, 1 and when added to the carry 1, it is 0 and sum is 0 and carry is 1, and carry is again forwarded. Now there is 2 zeros, that means 0 plus 0 plus 1, that means the sum is 1 and carry is 0. In this way, the first number is 1 1, that means 3, and second number is 1, that means 3 plus 1 4, and it is written here 1 0 0. 1 0 0 means 4. Binary equivalent, decimal equivalent of the 1 0 0 is 4. Let us take another example. For example, 1 0 1 0, this is the first operand, and 1 1 0 is the second operand. 1 0 1 0 equivalent to 10 and 1 1 0 is equivalent to 6. Now when he added 0 plus 0, that is 0, and 1 plus 1, that means 0, and carry is forwarded here. Similarly, 1 plus 0 plus 1, that means 2. 2 means 1 0. 1 0, that means carry is 0 and sum is 0 and carry is 1. This carry is forwarded. Now 1 plus 1, again it is 2, that means 1 0. 1 0 means the sum is 0 and carry is 1. Now here nothing is written, so we think that here is 0. So 1 plus 0 plus 0, that means 1. In this way it becomes 1 0 0 0 0, that means 16. When added decimal in terms of decimal additions, 10 plus 6 is equal to 16. Hence it is correct. Let us take another example. 0 plus 1, that is 0. Here there are two different numbers, 1 0 1 1 0 and 1 1 1 1. 1 0 1 1 0 is 22, equivalent to decimal equivalent to 22, and 1 1 1 1, that is 15. So result will be 37. Let us see whether it is coming as 37 or not. For example, 0 plus 1 is equal to 1, that is the sum is 1 and carry is 0, and again 1 plus 1, that is 0, and sum is 0 and carry is 1. Now there will be 3 ones, 1 plus 1 plus 1, that means 3. Now when we add 3 ones, that is 3, the 3 in decimal, that is 1 1 in binary. 1 1 in binary means 1 is carry and 1 is sum. As 1 is sum and 1 is carry. So 1 here, we place 1 here, also the carry is also 1. So this is the one thing. When we add 3 bits, which are all ones, then it is carry will be 1 and sum will be 1 and carry will be 1. Again there is 2 ones, that is 1 plus 1, that is carry, sum is 0 and carry is 1, and then 1 plus 1, again it is 0, therefore sum is 0 and carry is 1, carry is forwarded here, and as there is no nothing is written here, that means 0, that is 1 plus 0 plus 0, that is 1. So it become 37. When you convert the binary numbers, its decimal equivalent will be 37. Next is binary subtraction. In binary subtraction, if there are 2 bits, that is minuend and subtrahend, 0 minus 0, that is 0, 0 minus 1. In this case, in minuend, that is lesser number, and subtrahend, it is minus 1, that is larger. So we have to borrow 1. So here it is difference is 1 and borrow is 1. When 1 minus 0 is here, 1 is minuend and subtrahend, it is 1, and 1 minus 1 is equal to 0. In addition, there is sum and carry. In binary subtraction, there is difference and a borrow. Note that 0 minus 1 is equal to 1, borrow is 1. That means in the case of when there is 0 and in subtrahend 1, then therefore difference is 1 and borrow is 1. Let us take an example of binary subtraction. Here 101 and minus 011, that is 5 minus 3 is equal to 2. Now using the principle, here 101 and minus 011, in the middle, in the right column, it is 1 and 1, so 1 minus 1 is 0 written here. In the middle column, there is 0 and 1, so we have to borrow from the next column. So 1 is borrowed from here, and as 1 is borrowed here, so the left in the 0 is left here. In the leftmost column, the 0 will be left, since 1 is initially it is 1, but as 1 is borrowed, so 0 is left. So in the middle column it is 1 0, that means 2, and minus 1, that means 1. So it is 1 written here, and as 1 is borrowed from here, it is become 0. So 0 minus 0, it is become 0. So 101 minus 11, that means 5 minus 3 is equal to 2. Let us take another example. 1001, 111, that is 9 and 7, that becomes 2. Here 1 and 1, that the difference will be 0. Here 0 and 1 is written, so 1 should be borrowed here. From here 1 here borrowed here, and this is 0, so it become 1. But as here it written is 0, so again we have to borrow here. So borrow will be forwarded. So this is become 0, and this borrow is forwarded here. As we borrow 1 from here, so we have to cut it 1, and it become 0. So the result, the leftmost bit will be 0. In this way 9 minus 7 is equal to 2. Another subtraction process, 9's complement addition. It is an addition process, but it used in subtractions. How 9's complement is defined? For example, 512. 512 9's complement is 487. How it is calculated? If there is a 5 and we have to subtract from 9 this digit, so 5 plus 4 is equal to 9, 1 plus 8 is equal to 9, 2 plus 7 is equal to 9. Therefore 9's complement of 512 is 487. Similarly 9's complement or 487 is 512. The 10's complement of an integer is defined equal to 9's complement plus 1. Thus 10's complement of 512 is 488. That means 487 plus 1, that is 488. Decimal subtractions can be accomplished by additions of 9's complement plus 1 or addition of 10's complement as shown below. For example, 632 minus 246, that means 386. We use here 9's complement addition. 632 and subtract is 246. That means you have to complement this. 9's complement is 7, 4's 9's complement is 5, 6's 9's complement is 3. So the complement is changed and add their two numbers. 3 plus 2 is equal to 5, 5 plus 3 is equal to 8, 6 plus 3 is equal to 13. 6 plus 7 is equal to 13. Now add the carry. This carry is discarded and added at the end. It becomes 386. Hence it is also 386. It is also 386. That means we perform a subtraction process using addition. Similarly, it is represented in the form of 10's complement addition. Here 632 and 753 was 9's complement. When we add 1, it becomes 754. So 632 plus 754 is added and it becomes 1386. Now carry is dropped and we get 386. In this way we can find the subtraction value, subtracted value using either 9's complement additions or 10's complement additions. Tens complements process it is showing that tens complements. Example 1 is 003 minus 003. Its tens complement is 996, as 0 complement of 0 is 9. 3's complement is 6, so 996. It is when it's added 1, they become 997. This is 10's complement. Similarly, 214, 9's complement is 785, and when added, it becomes 786. So far, we have treated all our numbers as unsigned, positive only. To implement signed integers or signed fractions, we need a mechanism to denote the sign itself. Unfortunately, this introduces new problem. So we will see 3 different approaches, all of which add a special bit known as sign bit. If the sign bit is 0, the number is positive. If the sign bit is 1, the number is negative. If we have an 8-bit number, does this means that we need 9 bit to store it with 1 bit exclusively for sign. If we add 8-bit numbers, then we have to insert in another bit, sign bit. So total number of bit will be 9. We will see the signed integers additions, subtractions in the next slides. Now signed magnitude in 4-bit number. So for example, if it is written +3, then it is 0011. This is 011 is a magnitude and 0 is signed. If it is -3, then it become 1011. Notice that 4 bits we can store 16 numbers in unsigned magnitude. That is means 0000 to 111 or decimal 0 to 15. But in signed magnitude we can only store 15 numbers between -7 or 111 1 and +7, that means 011. So we have lost a number. Two problem is here. 0 is now represented in two ways, either 0000 or +000. Since in 4-bit representations, the sign bit we can represent 0 either -0 or +0. So when we use +0, then it become if it is a 4-bit representation, that means 3-bit magnitude and 1-bit sign, that is it is a sign bit, that is 0, that is +0 is represented here, and this is the magnitude. If it is -0, then it is 1 and rest of the bits is 0. So we have to represent, we have to take two different representation to represent a 0. So we lost the ability to store an extra number, since we have two zeros. Since there are 16 different possible values of binary digits, if we use this 100, so we will lose to represent a digit in this system. We cannot do ordinary arithmetic operation using signed magnitude. We have to strip off the signed bit, perform the operations, and insert the signed bit on the new answer. This is the required answer of the hardware. Whenever we take any calculations, perform any calculations, we need not use the signed bit as we need not include the signed bit for the calculations, since it gives the wrong result. So we strip off the signed bit and perform the operations. Then again insert the signed bit in the new answer. How to create a negative number? In digital electronics, you cannot simply put a minus sign in the front of a number to make negative. You must represent a negative number in fixed length binary number system. All signed arithmetic must be performed in fixed length number system. A physical fixed length device contains the fixed number of bits, usually 4 bits, 8 bits, 16 bits, to hold the numbers. At first, ones complement representations. An alternative approach to signed magnitude. Previously we say that if we insert if we have a positive number, then we use a 0 in the sign bit, and if it is a negative number, then we use a 1 in the sign bit. But there is another techniques to represent the negative numbers. It is known as a ones complement. How ones complement is represented? And negative numbers are stored differently from positive numbers. Positive numbers are stored as usual. Negative numbers, all bits are inverted. That is, 0 become 1s and 1s become 0. For example, if we represent plus 19 in 6 bits, then it is 0, 1, 0, 0, 1, 1. And if we represent minus 19, then all the bits are complemented. That is inverted. The 0 is complemented to 1, 1 is inverted to 0, 0 is inverted to 1, 1 is inverted to 0, and 1 is inverted to 0. In this way, minus 19, whenever we represent negative numbers, all the bits are complemented. This is known as ones complement representations. One complements representations for positive numbers is as usual what is written, that is not inverted, but in the case of negative numbers, all the bits are inverted. The first bit is not only sign bit but also the part of the number. Notice that we still have two ways to represent 0, 0, 0, 0, 0 and 1, 1, 1, 1. There are two ways of representations. If we use ones complement representation, then for plus 0 it will be 0, 0, 0, 0, 0, and for minus 0 all the bits are complemented, that means 1, 1, 1, 1. So we would not use ones complement. Now we go to twos complement. Here is also positive number remains the same. Negative numbers derived by flipping each bit and then adding 1 to the result. For example, plus 19 in 6-bit representation. First bit is a sign bit and 1, 0, 1, 1. So this is plus 19 representations, and minus 19 representation when it is complemented 1, 0, 1, 1, 0, 1. This is ones complement. Now add 1 to the ones complement. It become 1, 0, 1, 1, 0, 1, 1, 0, 1. When we represent minus 19 in twos complement, first find ones complement by inverting all the bits and then add 1 to the numbers. You get the twos complement. To convert back, flip all bits and add 1, we get the result. That means if we convert the numbers into minus 19, we will simply invert the number. That is 1, 0, 1, 1 is again converted to 0, 1, 0, 1, 1. It can be performed as in this way. At first add 1, then invert all the bits. You get the previous results. That is from where we start. We will reach at the point. While this is harder, it has two advantages. Since twos complement representations, we have to perform an extra calculations, but it has advantage only one way to represent 0. So we can store one extra values. Since if we take plus 0, then it is 0, 0, 0, 0. But when we take minus 1, then it is 1, 1, 1, 1, 1, and then again add 1 to the complemented bit, then it become again 0, 0, 0, 0. So in this way there is only one way to represent 0. Hence we use twos complement additions and twos complement representation for the hardware devices. In the hardware devices. Also, another advantage is arithmetic operations do not require filling of the sign bit. In the case of other two representation, we have to separate the sign bit for addition, subtraction, multiplication, division, etc. But in the case of twos complement, we have to we may include the sign bit in the arithmetical operations. The 4-bit representations, the decimal minus 8 can be represented as 1, 0, 0, 0, 0. Next 1, 0, 0, 1, minus 1, 1, 0, 1, 0. That is first bit is sign bit and another bit is complemented twos complement representations. In this way we can form a table. Here it is positive numbers. Only 0 is represented as 0, 0, 0, 0. 1 is represented here is 0, 0, 0, 1. So this all first bit is a sign bit. and here we can represent from minus 8 to plus 7. Let us take 83. 83 and minus 83 8-bit representations in all three signed representations. At first we can plus 83, that means it is simply 0 1 0 1, simply it is converted into binary. When it is represented in three different form in the case of negative numbers, we have to add an extra bit, sign bit, that is here it is an extra bit is added 1, and remaining bits are considered when we convert the numbers into binary system. It's written here. One's complement representation means all the bits are complemented, that is 1 is complemented to 0 and 0 is complemented to 1. 2's complement representation means an extra bit 1 is added. Similarly, we can convert the numbers into decimal numbers, into decimal integers in 4 representations. Unsigned magnitude representation, it is 242. Signed magnitude representation is minus 114. 1's complement representation is minus 13, and 2's complement representation is minus 14. By simply in the case of signed magnitude, we have to use a 1 in the case of in the place of sign bit, and it becomes 1114. Since this one is already present, we can consider this as a sign bit, and the remaining values, if we convert the remaining values, that means 1 1 0 0 1 0, it becomes 114. So this bits, if we represent in sign magnitude, it become minus 114. Similarly, 1's complement by leading bit is 1 and the number is negative, flip all the bits, so it becomes 1 becomes 0, there is 4 ones, 0, then 1 1, then 0 1, that means it is 13. Similarly, after flipping all the bits, if we add 1, then it becomes 14. For example, here is some example. After getting 1's complement, we can find its complements, add 1. It is a 8-bit representations. Now there is some example how 2's complement addition is performed. For example, 9 plus 5. As the numbers are positive, so complement 2's complement is same as as it represented in binary system. That is, 9 is represented here 1001 and 5 is represented 101, and if it is 8-bit representation, some extra bit is added, it become 14. Simply using the binary addition rules. Now positive number and negative number. When negative number is smaller than positive number, it is this, for example 9 minus 5 is equal to 4. When you represent it in 8-bit, it become, now 5 is represented, minus 5 is represented here. Its 2's complement is 1 1 1 1 0 1 0 and 1 is added, so it become, this is 2's complement of minus 5. Now this 2 is added here, 1 plus 1 0, 0 plus 1, in this way we get 1 0 0. Now extra bit is discarded, that is 8 bit. Here 8 bit is 0, it is, so it is a positive number, and then last digit, that is most significant bit, is discarded from here. So the result is 100, and the sign bit is 0, so it is a positive number. Now positive plus negative, you get negative answer, since minus 9 and minus 5 plus 5, it is minus 4. How it is performed? At first the minus 5 is complemented, and 2's complement is find, that is 2's complement. 5's 2's complement is as it is. Again both are added. Now 8th bit is 8 bit is 1, so it is a positive. It is a negative number, and and it becomes 100. That means it is represented as minus 4. Now to check whether it is a minus 4 or not, again we have to complement the number, that is it is complemented. After complemented we get 1's complement, then again add 1, we get 4. So for negative, in the case of negative number, the beta is again perform 2's complements to get the required answer. Now both are negative, minus 9 and minus 5. Both are have a 2's complement. We add, here it is 1, and it is disregard as 8 bit. 8 bit is sign bit 1, so the answer is negative. So again we have to find the 2's complement of the negative number. It become 40. This is all about the binary additions and subtractions. Next we discuss the digital codes, then we come to binary multiplication and divisions. Thank you.